No discussion of acid and base chemistry is going to be complete without talking about pH. So in this section, we're going to look at pH. We're going to look at its relationship to things like Ka, and we're going to look at it in terms of its relationship between the acidity and basicity of a solution. So let's first start with water, which I mentioned before is amphoteric. It can act as both an acid and a base. And in the previous section, we presented both of these reactions. Here, the weak acid phosphoric acid, which is not one of the strong acids, and you can tell because this is an equilibrium reaction, is reacting with water. And it's an acid donating a proton to water. Said another way, water is acting as a base. In this case, we have methylamine, and it is accepting a proton from water. In this case, water is acting as an acid. So water can act as both a base and an acid. And because of that, water can actually react with itself. Okay, so here we have water liquid reacting with water liquid. One of these two waters acts as an acid and donates a proton to this one. We get H3O+. Since it donated a proton, what's left is OH-. And water is both a weak acid and a weak base, and this is an equilibrium reaction. It turns out we can write a K for this. But in this case, K, we give it a special one, Kw for water, is H3O+ times OH-. Notice there's nothing on the bottom. You may be asking yourself, why is there nothing on the bottom? Well, it's because it's products over reactants. Our products are both aqueous, but our reactants, neither of them are aqueous, or they're both liquids. So we actually don't put them. And it turns out that at 25 degrees C, the concentration of H3O+ and the concentration of OH- is 1 times 10 to the minus 7 molar, or just 10 to the minus 7 molar. And if we take this, 10 to the minus 7 molar times 10 to the minus 7 molar, we get this Kw, which is a value you need to know, 1 times 10 to the minus 14. So this is basically the autoionization constant of water, 1 times 10 to the minus 14, and it's labeled as Kw. Note that the concentration of H3O+ and OH- in a neutral solution, pure water, is 1 times 10 to the minus 7. If you've had a class before where you learned about pH and you learned that a pH of 7 is neutral, well, it is not a coincidence that this is 1 times 10 to the minus 7 and the pH of 7 is neutral. Let's take a look at this in terms of a dynamic equilibrium and how we can shift that equilibrium in terms of Le Chatelier's principle. So in water, any sample of water, water is reacting with itself to form H3O+ and OH-. Well, what can we do to shift this equilibrium? Well, if I add an acid, that acid's going to react with some of that water and make more H3O+. If more H3O+ is made, what's going to happen to the concentration of OH-? Well, when H3O+ is added artificially by adding an acid, it's going to shift the reaction in this direction towards the reactants, right? From Le Chatelier's principle, we stress the equilibrium by adding more H3O+, and the reaction responds to remove H3O+, and the only way a reaction has to do that is to make more water. Well, what's definitionally going to happen to the concentration of OH- when that happens? Well, the concentration of OH- is going to go down. Why? Because some of it is reacting with H3O+ to form more water. So in an acid solution where we add something like H3PO4 and we artificially increase the concentration of H3O+, so in an acid, the H3O+ concentration goes up and the OH- concentration goes down. Note that in a neutral solution, these are both 1 times 10 to the minus 7 molar. But in an acid solution, as the concentration of H3O+ goes up, the concentration of OH- goes down. What about in the case of a base being added? Well, when a base is added, we artificially increase the concentration of OH-. If the concentration of OH- increases, this again shifts this reaction to form more water molecules. And when it shifts to form more water molecules, it needs to use some H3O+ to do that. So as the concentration of OH- goes up, the concentration of H3O+ goes down. So if we were to add the total height of this line and 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 this line, they'd all be at the exact same height, right? The total height of this on top of this and this on top of this and this on top of this are going to be the same. But in an acid solution, there's more H3O plus. In a basic solution, there's more OH minus, which may be something you are already familiar with, but you may not have heard it described in exactly this way because of Le Chatelier's principle driving this reaction back towards the reactants. And if there's excess of this, it means you're going to lose some of this. And if there's excess of this, it means you're going to lose some of this. You have to, because it's going to drive the reaction towards the reactants. So how does this all relate to pH? Well, if we look here, the concentration of these things in a neutral solution is 1 times 10 to the minus 7 molar. In an acid, the concentration of this is greater than 1 times 10 to the minus 7 molar. In a base, the concentration of OH minus is greater than 1 times 10 to the minus 7 molar. Note that because these are to the negative exponents, if this is 1 times 10 to the minus 2, that's greater than 1 times 10 to the minus 7. You have to be careful, all right? Because that's it's going to have less zeros between the number and the decimal point, essentially. So 1 times 10 to the minus 2 is 0.01. 1 times 10 to the minus 7 is 0.00000001, whatever it is. Okay, so that's basically how that works. So what can we glean from this from pH? First of all, if you have an acidic solution, the concentration of H3O plus must be greater than 1 times 10 to the minus 7. It doesn't have to be this much greater, it could be this much greater. The concentration of OH minus has to be less than 1 times 10 to the minus 7. So in an acid, H3O plus will always be higher, OH minus will always be lower. In a base, it's exactly the opposite. H3O plus will always be less than this line, less than 1 times 10 to the minus 7, and OH minus will always be higher than this line, will always be greater than 1 times 10 to the minus 7. So by knowing the H3O plus or the OH minus concentration, you can predict whether a solution is acidic or basic. And in fact, we'll do that several times in a minute. The other thing is, you see these numbers are not super convenient, right? 1 times 10 to the minus 7 or 6 times 10 to the minus 4 or whatever for the concentration of H3O plus or OH minus. How do we convert that into a convenient number? The pH equals the negative log of the H3O plus concentration. And this typically has values between 0 and 14. Now, if this is 1 times 10 to the minus 1 molar, the pH will be 1. If it's over here and it's 1 times 10 to the minus 13 molar, much smaller than 1 times 10 to the minus 7, the pH will be 13. It's much easier to deal with pH numbers than it is to deal with these concentration numbers, which is why we use the pH. The P of anything is the negative log of that thing. The P of H is the negative log of H3O plus. The P of OH is the negative log of OH minus. If you wanted to reverse this, if for example, you're given a question where you're given the pH and you need the H3O plus concentration for some reason, you would want to take the inverse log on your calculator shift or second log to the negative pH. Make sure you make the pH negative. Okay, so then it'll take it 10 to the negative pH, and that will give you the H3O plus concentration. Same for OH minus. Since the concentration of H3O plus times the concentration of OH minus equals to Kw, which equals 1 times 10 to the minus 14, we can also add the pH and the pOH, and they'll equal 14. If we took the pKw, it would be 14. And here, because you have exponents, instead of multiplying, you're adding. Okay? So this is basically some mathematical stuff that we'll need. So I always believe, as you've probably seen here, it's much easier to learn this stuff by example than me just spouting off a whole bunch of numbers that are hard to follow on a slide. So what I'd like to do now is go through several examples where we apply this logic in order to figure out whether solutions are acidic or basic, what is the concentration of something or something else, and so on and so forth. So let's go ahead and do that. But I should have mentioned before we do that, let's just look at some common things and look at their pH and pOH. The first thing to notice here, as the pH increases from 0 to 14 or 15, okay, or negative 1 to 15, usually we think about it between 0 and 14, but you can certainly have negative pHs for strong acid solutions, okay, the pOH decreases. So they're opposites. 0 is to 14, 1 is to 13. Said another way, if I added these up across every line, every single one of them would add up to 14 because the pH plus the pOH equals 14. Now let's look at some common things. Pure water has a pH of 7. Okay, baking soda, all right, is going to have a pH a little above 8. Milk of magnesia, which people take if they have an upset stomach, has a pH a little above 10. 1 molar sodium hydroxide, which you may have used in the lab, has a pH of 14. Now let's go on the other side. Lower pHs, acids. Coffee is relatively acidic. It has a pH of around 5. Orange juice is even more acidic, a pH 4 point something. Or stomach acid, a little over, close to 3, but above 2, between 2 and 3. 1 molar HCl has a pH of 0. So if the pH is less than 7, you have an acid. And if the pH is greater than 7, you have a base. And if the pH is exactly 7, you have neutral. All right. Note that the pOH scale is exactly the opposite. It's not that commonly used, but if you're wondering, a pOH of greater than 7 is an acid, and a pOH of less than 7 is a base. We will use the pOH, and we will mathematically use it to calculate things, but we don't typically think of, what's the pOH of coffee. You might think of what the pH of coffee, that's just more common. Okay, so now, as I ranted about how we do a bunch of problems and then put a slide in between because I forgot about it, let's actually do some problems. It says, let me switch over to the camera so that way I can write on it. It says, what is the H3O plus concentration for a solution with an OH minus concentration of 2.73 times 10 to the minus 2 molar? Is the solution acidic, basic, or neutral? So we have 2 questions here, and I'm actually going to answer the second question first. So the OH minus concentration is 2.73 times 10 to the minus 2 molar. What we want to ask ourselves is that greater than or less than 1 times 10 to the minus 7? Be careful. This number is greater than 1 times 10 to the minus 7. So concentration of OH minus is greater than 1 times, I'll put 1.0 times 10 to the minus 7. That means the solution is a base. We don't need to do any math. We don't need to calculate pH, although pH is more convenient. We don't actually need to do that. This solution is basic because this number times 10 to the minus 2 is greater than times 10 to the minus 7. Note if this was times 10 to the minus 9, then it would be less than. So the greater the negative number here, the smaller the number is because there's more zeros, 0.000009 zeros instead of 0.00, there'd actually only be 1 because we have to move this once, right? And then there'd be 1 more. So it'd be 0.0273. All right. That's that. Now, what is the concentration of H3O plus? Well, remember, Kw equals concentration H3O plus, concentration OH minus. For either one, okay, because we're going to use several of these, in this case, we want the concentration of H3O plus, so we divide by OH minus. Concentration of H3O plus equals Kw divided by concentration of OH minus. All right. Note that if you wanted the other one, the concentration of OH minus equals the Kw divided by the concentration of H3O plus. It doesn't matter because they're both multiplied, so you're just going to divide by the one that you have and leave the one that you're looking for on the other side. But mathematically they're the same thing. Well, Kw is a constant, so we can plug that in. 1 times 10 to the minus 14 over concentration of OH minus, which is 2.73 times 10 to the minus 2. And when we do that math, we find that it is 3.68 times 10 to the minus 13. All right, so this is the concentration of H3O plus. Let's take a look at the next one. It says, what is the OH minus concentration for a solution with an H3O plus concentration of 8.99 times 10 to the minus 5 molar? Is the solution acidic, basic, or neutral? So we need to look at the H3O plus and we need to compare it to 1 times 10 to the minus 7. In this case, the concentration of H3O plus is greater than 1 times 10 to the minus 7. So since this is a greater concentration than 1 times 10 to the minus 7 and it's H3O plus, this is going to be an acid solution or acidic solution if you prefer. Okay, now we need to calculate the concentration of OH minus. Well, we do this the exact same way. All right, so concentration of OH minus equals Kw, which is 1 times 10 to the minus 14, divided by 8.99 times 10 to the minus 5. And when we do that, we are going to get 1.11 times 10 to the minus 10 molar. Okay, when it comes to sig figs, I consider that this constant has however many you need, so I write my sig figs based on the number of sig figs in the number given. All right, so there's 3 here, so I put 3 here. So that's how we would do this one, very similar. All right, number 3, a little bit different. It says, what is the pH and pOH of a solution with an H3O plus concentration of 6.79 times 10 to the minus 11 molar? Is the solution acidic, basic, or neutral? Well, the first thing we want to do here is we want to determine whether it's acidic, basic, or neutral. So in this case, the concentration of H3O plus is less than 1 times 10 to the minus 7, which means that this is a base or basic solution, because 10 to the minus 11 is a smaller number than 10 to the minus 7, so therefore this is a basic solution. Now there's lots of ways to do this, all right, to find the pH and the pOH. But the way I'm going to do it is to find the pH and then to find the pOH from the pH. So the pH equals the negative log of the H3O plus concentration. Remember, P means negative log of, all right? We have pKa, pH, pOH. You don't want to have to learn those as 7 different things or 3 different things, all right? It's just a negative log of whatever it is. So in this case, we want to take the negative log of 6.79 times 10 to the minus 11. And when we do that, we find that it is 10.168. All right, so this is the pH. Note the sig figs here. This is 3 sig figs. This is 3 sig figs as a pH. This is not significant. This 10 is basically this number. Okay, it's not 11 here because this is greater than 1 times 10 to the minus 11, so it's 10, but this 10 is this number. These don't count as sig figs. So this is 3 sig figs, this is 3 sig figs. The truth is that the likelihood of you seeing a question on a test that differs by sig figs are not that high, but it is important to point out. All right, so this gives us the pH. Remember before, based on this information, we said it's a base. Based on this information, we can still say it's a base, right? Greater than 7, pH of greater than 7 is a base. This holds true. Now to do the other one, pH plus pOH equals 14. Said another way, pOH equals 14 minus the pH. Note again that you could have found the OH minus concentration, similar to how we did up here, and then taken the negative log of that to find the pOH. It's one extra step, but it's not wrong. Okay, it totally would work. So, if you're more comfortable with that, you could do it that way. So in this case, we're going to take the pOH equals 14 minus the 10.168, and when we do that, we get 3.832. Again, notice that this 14, I consider it has as many decimal points as it needs, 14.0000. So if this has 3 decimal points, I'm going to report my answer to 3 decimal points. Just the sig figs are a little bit tricky here when you're taking logs and things like this. Again, I doubt you're going to see any questions where the answers are different by just sig figs. All right, let's take a look at the next set of problems. So, similar, it says, what is the pH and pOH of a solution with a concentration of OH minus of 3.84 times 10 to the minus 7? Is the solution acidic, basic, or neutral? So I'm going to, again, like usual, do the acidic, basic, or neutral thing first. So in order to do that, I'm going to do concentration of OH minus, and I'm going to compare it to 1 times 10 to the minus 7. 3 times 10 to the minus 7 is bigger than 1 times 10 to the minus 7. When the two exponents are the same, you're comparing the number on the outside. 3.84 is bigger than 1. So this is greater than 1 times 10 to the minus 7. And since it's OH minus, that means this solution is a basic solution. All right. Now that we have that, I need to find the pH and the pOH. And I'm going to do it exactly the same as I did before. I'm first going to find the pOH, which equals the negative log of the concentration of OH minus. So the previous example, it was more convenient to me to find the pH first because I was given H3O plus. Here, it's more convenient to find the pOH because I'm given the OH minus. So the pOH equals the negative log of 3.84 times 10 to the minus 7. The pOH, in this case, is going to equal 6.416. Again, 3 sig figs here. These are 3 sig figs. This 6 and this 7 are related to each other. This isn't a sig fig. It's a placeholder once you take the log. All right. Now I need to find the pH. Well, the pH plus the pOH equals 14. And very similar to before, the pH equals 14 minus the pOH. Before it was 14 minus the pH equals the pOH. It's the same thing. So the pH equals 14 minus 6.416. The pH is equal to 7.584. Again, comparing the basicity, pH is greater than 7, so it's a base. Or the pOH is less than 7, so it's a base. I like the pH because I'm more familiar with that, but the pOH works as well. All right. Next question. It says, what is the concentration of OH minus in a solution with a pH of 10.47? There are lots of ways to answer this question. I'm going to show you one of them. The first thing I would do is the pH plus the pOH equals 14, or the pOH equals 14 minus the pH, which we used in the previous question. All right, not this previous question, but one more previous to that. So in this case, the pOH equals 14 minus 10.47, and the pOH is equal to 3.53. Now, remember that the pOH equals the negative log of the concentration of OH minus. If you want to reverse this, you're going to take the negative over here. So negative pOH equals log concentration OH minus, right? I multiply both sides by -1. Then to get rid of the log, we take the inverse log, 10 to the log, or 10 to the negative pOH. So the concentration of OH minus equals 10 to the negative pOH. If you wanted the one for pH, it's concentration of H3O plus equals 10 to the negative pH. All right, they're the same. I derived this for you, but you can think of it as a separate equation if you prefer. I put it on the previous slide. So to find concentration of OH minus, we need to take 10 to the negative pOH. So in this case, the concentration of OH minus equals 10 to the negative 3.53. And the concentration of OH minus equals 3.0 times 10 to the minus 4. All right. The same idea applies here. This is only 2 sig figs, so this can only have 2 sig figs. Again, I don't think you're going to get questions where the answers are only different by sig figs, but I'm just pointing out that that's how sig figs work with logarithms. All right, now let's look, kind of combine these two ideas. So in these previous two examples, we are looking at examples where we essentially have pHs and pOHs, but we're not considering an acid-base equilibrium or an acid equilibrium or a base equilibrium. In fact, we're not going to consider any base equilibriums until a little bit later on in this chapter. But what we are going to do now is combine these two ideas, the idea of pH and the idea of equilibrium. So I mentioned in the previous chapter how important it was to learn how to work with these ice tables, and we went through several examples. Well, here's them coming back, and they'll come back again in the next chapter. So it is really important that we learn this. It says, what is the concentration of H3O plus and pH of a 0.180 molar HF solution? And then it tells us the Ka of HF. So as I did in the previous example, I set up the ice box here so it might be a little bit neater, but you could set this up yourself. So remember that in an iced box, we're going to have initial, change, and equilibrium. And we're going to put everything in the ice box that it goes in the Ka expression. So in this case, we have HF, because it's aqueous. We don't have water because it's a liquid, so we don't put it in the Ka expression, so we don't need to put it in the ice box. We have H3O plus, which is aqueous, so we put it here, and we have F minus. And then our Ka is going to be our products over our reactants. Well, let's look at this solution. At the beginning of the day, we have 0.180 molar HF. Okay? We have no H3O plus, and we have no F minus. So the instant this is added, we have this as our initial concentration. We don't have any H3O plus and we don't have any F minus, so we're starting only with reactants. Well, how much of this and this are we going to gain? I don't know. So we're going to gain X of this and X of this. How much of this are we going to lose? Well, because the stoichiometry is 1-to-1, that's why we get 1x of this and 1x of this, we're going to lose 1x of this because one of these forms one of these and one of these. So we get x of these, we lose x of this. At equilibrium, we're going to have 0.180 minus x. Here we're going to have x, and here we're going to have x. Now, as I mentioned before in the previous chapter, the idea here is we can ignore this x if this x is less than 5% of this one. That being said, I'm not going to give you examples where it's not. So in this case, we can ignore this x. So I'm just going to put at equilibrium that this is 0.180, which again avoids us having to use the quadratic equation, which makes our life a little bit easier. So now let me write the Ka expression. Ka equals products. First product is H3O plus. Second product is F minus over reactants, HF. Note, Ka and Kc are the same. If I could call this Kc, you don't call this Kc because it's a special case where we have an acid, but this is the same as Kc. This is nothing new. All right, now I have a Ka value. Sorry, it's not on the screen. I have a Ka value, and I have variables and one value here. So I'm going to plug in what I know. So I'm going to put in 3.5 times 10 to the minus 4, which is a Ka, which is given to me in the problem, equals the concentration of H3O plus at equilibrium is X, times the concentration of of F minus is also X, and the concentration of HF is 0.180. Cross multiply and combine the x's, so x squared equals 3.5 times 10 to the minus 4 times 1.80, which is, or excuse me, 0.180, which is equal to 6.3 times 10 to the minus 5. Take the square root, take the square root. X equals 7.9 times 10 to the minus 3 molar. Now, if this were in the previous chapter, this is what I would do. I would write concentration of H3O plus equals concentration of F minus equals 7.9 times 10 to the minus 3 molar. But in this case, I'm not asked for that. I am asked for the pH. So there's an added step. All right, and the added step is, well, this is the concentration of H3O plus. How am I going to find the pH? Well, the pH is equal to the negative log of the concentration of H3O plus. So this is exactly what I did before. I'm just adding one little step at the end. So if you practice this before, it's going to pay off now because you already know how to do this. So now I'm going to take negative log of this one, 7.9 times 10 to the minus 3. And when I do that, I find that the pH is 2.10. All right, so this is my final answer. So HF here is behaving as a weak acid, and it's lowering the pH to 2.10, which is less than 7. All right, last example, kind of the same thing except backwards. All right, it says the pH of a 0.185 molar weak acid solution, HA, is 3.09. What is the Ka of the acid? All right, so this is basically the same type of question except it's backwards, and it takes a little bit of practice to realize this is the same question asked backwards. So I am going to use the initial change and equilibrium, but I'm not going to do this in the same way. So in this case, I'm given a few things here as far as the initial concentration. The initial concentration of HA is 0.185 molar. Okay. The concentration of H3O plus and A minus at first seem unknown, but believe it or not, they're not unknown. Well, the concentration of H3O plus in this problem is given, but it's not given as a concentration of H3O plus. It's given as a pH. So I need to convert this into a concentration of H3O plus. Specifically, I need to take concentration of H3O plus equals 10 to the negative pH, which in this case equals 10 to the negative 3.09, which equals 8.1 times 10 to the minus 4. I'm going to pause the video for a second and get those extra decimal places. Never mind, I don't actually need them. This is 2 sig figs and this is 2 sig figs, so this is good to go. All right, so this is the concentration of H3O plus. But let's think about what's going on, okay? So at the beginning of this reaction, HA is the only thing in solution. So the initial concentration of this is 0, and the initial concentration of this is 0. When the reaction reaches equilibrium and I measure the pH, I've added 8.1 times 10 to the minus 4 molar H3O plus. How much A minus did I add? Just like before, this was plus X and plus X because there's a 1-to-1 stoichiometry. I have to add the same amount of A minus because there's one of these and one of these. Note if they weren't 1-to-1, that wouldn't be true. But because they're both 1-to-1, I'm going to add also 8.1 times 10 to the minus 4. And over here, I'm going to subtract 8.1 times 10 to the minus 4. Now here we get into a little bit of a disagreement, let's say, where different people are going to teach this a different way. Some people are going to say you should take this 0.185 minus 8.1 times 10 to the minus 4 to find the equilibrium concentration of HA. And that is a 100% valid and reasonable thing. I'm going to say that because this is less than 5% of this one, you can ignore it just as you would ignore it if it's an X. Is there a true right and wrong way to do it? I don't know. It might be more right to actually subtract it. But it's certainly easier to ignore the X because you don't have to use the quadratic equation. And I think that there's enough to learn here. So I'm just going to say we can go ahead and ignore this and just say that the equilibrium concentration of HA is 0.185 with the full understanding that other people are going to say that's not the right way to do this. Okay. And I agree with them. All right. So I'm not saying they're wrong and I'm right or anything like this. I'm just saying that there's different ways to do this. I'm going to say we can ignore this because we would ignore it if it was a minus X. In this case, we have 0 plus 8.1 times 10 to the minus 4, which of course is just 8.1 times 10 to the minus 4 because we're just adding 0 and this on this end. All right. Now I can write my Ka expression. Ka equals concentration of H3O plus at equilibrium, concentration of A minus at equilibrium, divided by concentration of HA at equilibrium. Now I can plug in my equilibrium concentrations, which are all numbers, so there's no X here. I'd have to be given Ka if there was, but I have 8.1 times 10 to the minus 4 times 8.1 times 10 to the minus 4 divided by 0.185. And when I do all that work, I find that the Ka of this particular acid is 3.5 times 10 to the minus 6. So we've now applied pH, pOH, concentration of H3O plus, concentration of OH minus, and then we took those concepts and applied them to equilibrium reactions. In the next section, we'll look at percent ionization, and then we'll look at what happens with bases. In the next chapter, we'll start to move this in another direction where we start to mix the acids and bases together, and things get a little bit more complicated when that occurs.